Okay, so good evening, everyone. My name is Avik Mukhopadhyay, and I'm a PhD research scholar at the Department of Electrical Engineering at IIT Madras. And we are in the 11th live session of Multirate Digital Signal Processing. And in this session, we will be covering some sample questions that were covered in the 11th week of the course. So in the 11th week, mostly the concepts of OFDM, which is orthogonal frequency division multiplexing, was discussed. We looked at different properties of the circulant matrix, such as the diagonalizability and so on, and also we saw the use of the cyclic prefix, zero padding, and those things. So mostly this will be a review of the lectures because the concepts were mostly theoretical, and we'll also look at some numerical examples as well. But mostly it's like a revision of the lectures also. Okay, so let's get started. I hope I am audible and my screen is visible to you. So this is Multirate DSP, and we are in the 11th session, so covering week 11 contents. And let's start with the first question. Okay, so in the first question we are asked which of the following will be true for a circulant matrix. So in fact we have looked at the definition of a circulant matrix. In fact, I covered the circulant matrix, pseudo-circulant matrix, or the Toeplitz matrix, the structure. How do the columns look like and what are their properties. I have covered them in detail in the last week's session as well. So in case you are not familiar with it, you can just watch the previous session that I uploaded last week. And so this is also a question related to the circulant matrix property, and we have seen this in the lectures. This is directly from the lectures as well. So we know that, okay, as the name suggests, also circulant, so there is a circular shift property which is going on in the matrix. What happens is that you can either think it row wise or column wise, whichever way. If you think column wise, then is the first column of the matrix that can have any arbitrary entries, and it's a square matrix, and in the second column will be the circular shift of the first column. Okay, so each element of the first column gets shifted downwards by one unit, by one place, and it's a circular shift, meaning that the last element of the first column now comes way back to the first element in the second column. So that's why it's a circular shift. Okay, and similar thing happens for the successive columns as well. So meaning that the third column is a circular shift of the second column by one place. The fourth column is a circular shift of the third column by one place. So every column from starting from the second column onwards is a circular shift of its preceding column by one place. That's the property. Okay, and so the observation is that the first column can be arbitrary, as I mentioned. So option A holds true, and as I said, option B, which states that columns other than the first column are circularly shifted, which is true, which is the case. And it also turns out that circulant matrix have the property that they are always diagonalizable. We have seen them in the lectures also. We have expressed the circular matrix as a product of three matrix, where we had the IDFT matrix followed by diagonal matrix and then the DFT matrix. So indeed it is a diagonalizable matrix. So all the three options A, B and C hold true, and so option D, which states all of the above, is the right option for this question. So it's purely theoretical, but still I'll write down everything, so it will be a revision for you guys. So if I have a matrix, let me label it by A, and I'm giving this bar beneath the letter just to indicate that it's a matrix, or in general a vector. So you can think a vector to be a column matrix as well, or a row matrix as well. So this has the following entries. So if you look at the first column, the first entry is A0, then we have A1, so on, all the way till A m minus 1. So there are m entries. So this matrix has m rows, and similarly it should have m columns as well in order to be a square matrix. So now this is the first column that I wrote. The second column would be a circular shift of this entire column by one place downward. So meaning that this A0 here, which was sitting here, will now come down by one place in the second column. This A1 similarly will come down by one place here. Okay, and it will go all the way till, and in the second column the last entry would be am minus 1, sorry, am minus 2, and the entry which is am minus 1 will now go back to the first place here like this. Okay, so meaning that the am minus 1 term will be circularly shifted, okay, from the bottom to the top. So this is how the shift is happening, and so on, you know, it goes on until this, you know, until this A0 comes at the last place at the bottom of the matrix. So this will result in a m cross m square matrix. So what about the last column? So this continues like this. So in the last column we have A0 sitting here. So all the, if you observe the principal diagonal of this matrix, all the elements of the principal diagonals are is equal to A0. And in fact, if you observe any of the diagonals other than the principal diagonals also, the entries are constant. So sometimes these circulant matrix are also known as some constant diagonal matrix. So that apart, coming to the last column, so A0 appears here in the last column. So its successive elements like A1, A2 now come to the top. So A1 will come here, followed by A2, so on till A m minus 1, right? So this is the structure of the circulant matrix. So this is a circulant matrix. By the way, I hope I have unmuted myself. Okay, yeah, it's fine. Right. So so the first column, what is the first column of this matrix? This is the first column, right? this is the first column of the matrix, and it can be arbitrary. It can be arbitrary. The rest of the columns are depending on the first column, right? So once you have the first column, you can automatically generate the rest of the columns from that. So the observation is that this, oops, sorry, yeah, so this first column can be arbitrary, which is true. So that was our option A. So option A is true. And the observation here is that the second row, the second column, meaning that this column, oh, maybe I should use a different color. This column this column is a circular shift of the first column by 1 unit, because you see these elements, this A0 is going down here by 1 place, this A1 is going down 1 place here, and so on, right? So that's the observation. So the observation is that second column is the circular shift of the first column by 1 place. Okay, so that is the idea, and it is shifting downwards. Okay, the elements are going downwards by 1 place, and similarly you can repeat this pattern, and you can generalize a statement that the ith column of this matrix is the circular shift of its preceding column, which means I minus 1th column by 1 place. And here this index I runs from, it starts from 2, because the shift starts from the second column onwards. So 2, 3, so on till the last column, which is the mth column, right? And also what we have seen, so this means that, like, therefore columns other than the first are circularly shifted. So this is true. This is also true. Okay, this was option B. Finally, regarding diagonalizability, which was our option C, that also holds for a circulant matrix, we have seen. So I'll write the basic form. So this matrix, I use the notation A bar for the matrix, for the circulant matrix. So this can be expressed as the product of these three matrices. So W Hermitian times gamma times W, where, so it's a product of three matrices. So where W is the normalized DFT matrix. We have seen the DFT matrix, right? It's a square matrix, and it has the entries in the form of the complex roots of unity, and this W matrix is a normalized DFT matrix. So which means there will be a scaling factor of 1 by square root m in front, and the entries are like this: Wm to the power km. Okay, so this W, I'm coming to this W suffix m thing. It's actually the mth complex root of unity. I'll write it down here also. So Wm here, it means e power minus j 2 pi by m. Okay, the mth complex root of unity, and this W matrix is the normalized DFT matrix. Okay, right. And by the way, this Hermitian, this H denotes Hermitian, which is this is Hermitian or transpose conjugate. Okay, and so this is the W matrix. And what about the second matrix, which is this gamma? So this gamma is actually a diagonal matrix. So that's why the diagonalizability is being satisfied. So this matrix A can be expressed in this form, where the matrix sitting in the middle in the product of three terms turns out to be a diagonal matrix. And this gamma is a diagonal matrix, meaning that the entries of the principal diagonal are non-zero. All the other entries are zero. So the principal diagonal runs as follows. So it runs from here. So let's say the first entry is gamma naught. Then we have gamma 1, and so on till gamma m minus 1. So all these three matrices, W, gamma, and W Hermitian, all are m cross m matrices. So this is how it looks, and so you can think like the rest of all the entries are zero. Okay, so I am not putting any entry. That means that those entries are automatically zero. Okay, so this is a gamma is a diagonal matrix. Okay, okay, so W, I'm just writing the dimensionality. It is m cross m. Gamma is also m cross m. W Hermitian is also m cross m. Okay, so the overall A matrix is also m cross m. Okay, okay, great. And if you want to know about this entries in the diagonal gamma i's, so this gamma m's, sorry, this gamma m's are the entries along this diagonal, this diagonal, this diagonal. So gamma m's are the DFT DFT. Okay, they are the DFT of the first column of your original circulant matrix, which was that A matrix. So this first column, highlighted in orange color. Okay, yeah, the first column, orange or brown color, whatever. So using those elements, you're taking the DFT of that column, of that first column, to obtain these gamma naught, gamma 1, and so on till gamma m minus 1. Okay, so these are the DFT of the first column of the circulant matrix. Okay, A. So meaning that okay, I'll go to the next page. Maybe I can write it here as well. So meaning that this gamma m is nothing but you're taking the DTFT, right? Sorry, DFT, right? So this AK is the kth, or rather the k plus 1th entry. So AK corresponds to the k plus 1th column, right? So you can imagine, right? So this times you have that DFT formula, right? E power minus j 2 pi k n by n. So this can be written as follows, where k runs from 0 to m minus 1, because there are m minus 1 such terms, right? Right, I think, yeah, I think I have written it correctly. Or should it be, uh, I'm not sure, I think it should be AM. Should it be AM or should it be AK? I think AK only. You can verify it, okay, later. So but the idea is that you take the DFT of the first column and obtain the diagonal entries, right? And another observation is that this DFT matrix is actually a Hermitian matrix, and W Hermitian is actually equal to W inverse as well. Okay, so it's a unitary matrix as well, and so all the three options are actually true, first three options, and which leads us to the conclusion that option D, all of the above, is the right answer. Okay, sorry for making this so crowded here, but yeah. Okay, so first question done. Now coming to the second one. See, all these are theoretical, I mean conceptual questions. So the second question says C circ, which is the circulant matrix. So here the standard notation is used. I think we use this notation in the lectures also. Here that bar in the bottom is just eliminated, but you can keep it as well. So C circulant is equals to W inverse times tau times W. That's what we saw, right? Just in the previous question in the diagonalizability, right? So instead of that A, we are using the C circulant notation here. If that is the case, and if C circulant inverse also exists, meaning that it is also invertible, is given, then which of the following is true for the inverse of the circulant matrix? So what is basically C circulant inverse? That's what you need to find. And again, this is the nothing special. So what we are given is C circulant equals to W inverse gamma W. That's the diagonalizability thing, right? And it is also given that C circulant inverse also exists. If the inverse exists, then only you can compute the inverse, right? So then we are asked to find what is the form for it, C circulant inverse. So um, so if I take inverse on both sides, so what happens? This is just basic linear algebra. So C circulant inverse, it becomes, you know, on the LHS we get C circulant inverse, and on the RHS we have this thing whole inverse. correct? And from the property we know that, so this is the LHS. On the RHS, how can we expand this RHS? This is some product of matrices raised whole raised to the power, whole raised to the power minus 1 or the inverse. So this can be actually written as follows. So you go from the right to left, right? So the rightmost thing is this W. So this W comes in the front and with an inverse. Then the second last is tau. Tau comes out with an inverse, and the first term, which is W inverse, also comes with the inverse. Okay, that's the law, because what's the rule I'm following here? Let's say if I have some product of three matrices A, B, C whole inverse, that can be written as C inverse times B inverse times A inverse. So in the reverse direction, you will have the product. Okay, right. And now what does this give us? C circulant inverse equals to W inverse times gamma inverse, and the third term W inverse whole inverse is nothing but W. So this is the form of the inverse. Okay, so W inverse tau inverse, sorry, gamma inverse times W, and I think it is matching with option B. Option B, W inverse gamma inverse W. So option B is the right answer. Again, easy question. Now let's move to the third one. Okay, in the third one, so it's kind of a extension of the second question. So consider gamma in the previous question, that diagonal matrix, uh, as follows. So the principal diagonal has these entries C2, C1, C2, so on till Cn. Okay, what are these C1, C2, Cns? These are basically the channel tap coefficients, right? Right. So and if this is the form for gamma, then what would be a correct implication of Ci equals to 0? Meaning that the ith entry of this principal diagonal, or in other words, the I comma I entry of this tau of this gamma matrix, the element that lies at the intersection of the ith row and the ith column of this matrix gamma, uh, is Ci, which is 0. If that happens to be true, so what does that mean? That coefficient is 0, which means that, so what happens in OFDM? You break up your uh, entire channel into sub channels, right? So that corresponding ith sub channel is getting 0 gain. So Ci for that ith sub channel is 0. So the channel gain is 0. So the frequency response for that ith sub channel is 0. So if the channel gain is 0, then if irrespective of whether you are sending some symbol from the transmitter, since your channel gain for that ith sub channel is 0, nothing will be transmitted to the receiver, right? The receiver will have nothing, so no signal will appear at the receiver because of this Ci going to 0. So that's one straightforward implication, that okay, we observe no signal at the receiver. Okay, and the problem here is that if you get a 0 at the receiver, you get no signal, there is no way you are able to recover what was the actual original transmitted symbol uh, from the transmitting end, because that got completely lost because of the channel gain being zero for that ith subchannel, right? Okay, so that's one thing. So option A is correct, no doubt. And another thing is, what option B is saying is ith subchannel is don't care. So we have even, I mean, encountered this terminology don't care also. So what it means is that so now you have to think from the perspective of water filling, the water filling concept. What happens in water filling? So in this situation, Ci is 0, meaning that the ith subchannel is in a very poor condition. So the channel gain is 0 for that ith subchannel. So it's like almost poor SNR condition. So what is the concept of water filling? What do we do? What strategy do we take for such poor channels or sub channels? We allocate zero power, right? We don't allocate any power, correct? Or in other words, so no power will be allocated to that ith sub channel, or in other words, no information or symbol will be transmitted on Si of n, right? If Si of n is the transmitted symbol through that ith subchannel, so we won't transmit anything. So that's how I'll actually save my transmitting power also, correct? And so under this condition, basically the ith subchannel behaves as don't care, right? We are not bothered about that channel anymore because we are not sending the information, right? There is no power allocation going on. Okay, so these two things are actually um, true. Okay, these two things are actually true. Okay, first, there is no signal at the receiver because there's no question of any signal at the receiver for that ith subchannel because the coefficient died, became zero. And secondly, by following the water filling strategy, we are not caring about that particular channel. We won't allocate any power. We won't invest our resource or power to transmit symbol through that ith sub channel because it's in a poor condition, poor SNR condition. So yeah, and so that ith sub channel is treated as a don't care sub channel, right? So option A and option B both are actually true. So option D, if you see, it states both A and B. That's the correct option. Okay, I hope you are able to understand. So in fact, this was discussed also. So as I said, it is mostly a recap of the contents, but I think that's a good idea nevertheless. So tau is here given in this form. I'll quickly write it. Okay, right. And now if you also try to visualize the frequency response of the channel. So frequency, what is that Ci equals to 0 meaning? Okay, what does that mean actually? So frequency response of the channel. So each sub channel, there is a concept of sub channels, right? So each sub channel is observing a different channel condition. So if I have a channel characteristics as follows, so that's the frequency response. So along the horizontal axis I have frequency, which is omega, and along the vertical axis, let's say I have the frequency response basically, or if I only take the magnitude, let's say the gain, so some c of e power j omega magnitude, and let's say it has this following kind of pattern. Goes down, fluctuates, and then vanishes here, goes to zero, then maybe starts to improve and so on. It's a random fluctuating channel. So now what we do is we break down the channel into sub channels, right? So let's say this is one sub channel like this. Okay, then we have, let's say, another sub channel like this. I mean, it's not drawn to scale, but I hope you get the idea. Another sub channel. And this is another sub channel. And so this channel, this particular sub channel that I drew just now, is the one, that ith sub channel, which actually witnesses a zero gain, you see. So ci for this is actually zero, the gain is zero. Similarly, you have other sub channels like this. So more or less a picture like this. So what are these things? These are your sub channels. And what is this particular thing? This particular sub channel is my ith sub channel in the question. So this is my ith sub channel, let's say. Okay, that is in the poor condition. Okay, so the first implication of ci equals to 0. Okay, so which means ith sub channel has channel gain equals to 0, as can be seen from this above diagram. So if the channel gain is 0, it means no signal is received at the receiver, right? No signal is actually received at the receiver from that particular sub channel, from the ith sub channel, even if some signal was transmitted from the transmitting end. So even if some signal, let's say psi of n, was transmitted from the transmitter, So that's that encompasses the first observation, which is there is really no signal at the receiver, and a consequence of this observation is that we can't recover what was the originally transmitted signal si of n for that subchannel, right? So because how can we do that? We are obtaining zero signal, no signal at the receiver, so we can't map it back to some transmitted symbol, so cannot recover the originally transmitted, just a second, signal which is si of n. Okay, and what else? Oops, sorry. Okay, what else are the observation? What else are the implications? As I said, and now if you look at it from the perspective of water filling, right? We'll do water filling in these kind of scenarios because the channel gain is varying across different subchannels. So since the gain of the ith subchannel, it went to 0, right? And it's given in the question, so I have drawn a illustrative diagram also just for your visualization. So what's going on, what does ci equals to 0 mean in terms of a diagram? Okay, so since the gain of the ith subchannel is 0, which means like poor channel condition, okay, poor channel condition, what does my water filling strategy tell me? It tells me don't allocate any power to that particular subchannel, so no power will be allocated to the ith subchannel. That is no information will be transmitted on that, I mean si of n, okay, that ith subchannel. So under this condition, under this constraint, under this condition, this ith subchannel behaves as a don't care, right? We are not bothered about it, okay? We are not taking that particular subchannel into our account. So the ith subchannel behaves as don't care, okay? So both option A and B were the correct answer. So option D is saying option A and B both are correct, which is the correct option. Okay, and then now we can move on to the fourth one. Okay, consider the following statements. There are two statements. Statement 1 is saying a zero forcing equalizer for a channel with Z transform C of Z is 1 upon C of Z. Statement 2 states that a zero forcing equalizer is likely to introduce noise enhancement. Now we have to find out which of the following options is correct, whether both the statements are true or not, whether statement 1 is true, statement 2 is true, and so on. What's the right combination? So, and again, this has been discussed in the lectures as well. So it is actually the zero forcing equalizer. The statement 1 is actually correct. We basically do the inversion of the channel, right? We take its reciprocal, but the problem is that, so this is the scenario. See, in the previous question we saw that, okay, ci, what's the implication of ci being equal to 0? So that's like a kind of an ideal situation where it is completely 0, but in a more practical scenario there could be some noise, there could be some minimum noise signal level, so which makes ci not exactly equal to 0. So there will be some small amount of non-zero gain for the ith subchannel. So it's some delta, you can assume, okay, delta tending to 0, but delta is not exactly 0 due to that particular noise. And so it's a very small quantity, but what you are doing is, for a zero forcing equalizer, you are taking the reciprocal of that, 1 upon c of z. So if c of z is very small due to that noise component, 1 upon c of z, which is the reciprocal, will overshoot to a very large value, and that noise is getting amplified, that noise is getting boosted up, which is undesired effect. So it is leading to noise enhancement as a consequence of that. So statement 2 is also correct actually, and statement 2 is actually a consequence of the way the uh, zero forcing equalizer actually works. So it's a statement 2 is actually a consequence of the statement 1 as well. But checking the options, actually option A is the right answer, because both statements are true. It is claiming both statements are true. That's the right option. Okay, yeah. So what do we have here? Okay. Okay, so so the channel, if you have a channel, by the way, before the channel there are, the transmission is going on, right? We have the m symbols, transmitted symbols, and then before we actually send it, we have looked at the concept of redundancy, right? So we are adding some mu number of redundant symbols, correct? And then so it becomes a m plus new block length, right? So after adding redundancy, and that is the one which is sent through the channel, and so those components are lying here, okay, in this stage. I am not drawing it, okay. So this is the channel, actually I'm drawing it from the channel uh, onwards. Now the purpose of the equalizer is to undo all the effects, uh, all the distortion that happens as a uh, signal is passed through the channel. So it kinds of that zero forcing equalizer does this thing. So it will basically do a channel inversion, 1 upon c of z. So that's my ZF equalizer. ZF stands for zero forcing. I mean, you can refer to any textbooks if you want to know this in detail. And so as I said, so in the previous question, ci equal to 0, that's like a very um, strict case, very what should I say, what term should I use, very ideal and specific case, and in practice Ci is actually not exactly equal to 0, so not exactly 0 due to noise. So you can take Ci to be some delta not equals to 0 due to the presence of noise. And now if C of z is very small, then what the zero forcing equalizer is doing is it is inverting the channel. Therefore, for a small noise also, it will be boosted up significantly, because if you take the reciprocal of a very small number, let's say you take the reciprocal of 0.001, it becomes 100, right? So it gets boosted up. So this becomes very large. Very large. So the noise gets boosted up. So therefore noise enhancement is actually the problem that is faced here. Okay, and which is exactly what was given in option A. I mean, option A captures the fact that both the statements, statement 1 and statement 2, both are correct, both are true, right? So our answer is option A. Both statements 1 and 2 are correct. Okay, again this was also discussed, so nothing fancy. And now, well, what can we do now? Okay, let's move on to the next one then. Okay, what do we have in the next one? Okay, which of the following, this is the fifth question, which of the following in which of the following block transceiver schemes will you see symbol estimation using pseudo inverse? So we have encountered this method of pseudo inverse, right? um, so we have seen cyclic prefix, we have seen zero padding, right? um, and in zero padding actually we have encountered this pseudo inverse, remember? Because what happened is that due to the addition of redundancy using zero padding, you are basically adding mu zeros, and as a result of which on the receiving on the receiver end, what happens is that you are getting some n capital N number of equations, but the number of unknowns is capital M, and capital M is less than capital N. You know that relation, right? Capital N is equals to capital M plus mu, right? Where capital M is the number of data symbols and mu is the number of redundant symbols or the zeros, which we basically are padding uh, in the case of zero padding. So that gives you a total block length of capital N, and so essentially you have an overdetermined system of linear equations, meaning that you'll have more equations than the number of unknowns, and such kind of equations are usually uh, solved using the least squares approach, and in the least squares approach, as you know, we take the pseudo inverse. Okay, uh, because see the I mean it's a rectangular matrix, right? So m and n are different, so that's why we go for a pseudo inverse, which is not exactly a inverse. We had that expression, right? C low matrix, remember? You take that C low Hermitian times C low whole inverse times C low Hermitian into R of n. That is the expression for your estimate of the transmitted vector, right? I'll just go through the notations in this question for the sake of your revision, but the answer to this question will be block transmission with zero padding. In case of cyclic prefix, what we have seen is due to that circulant nature, we are not having any concept of pseudo inverse here. We are straightforward, taking the inverse, C circulant inverse. Okay, and that's the case for cyclic prefix, but the pseudo inverse is valid in the case of zero padding. That's what we have seen. Okay, so zero padding is actually the scenario where we do this. For a block transceiver. For block transmission, because it's a data block, right? It's a collection of symbols. Okay. So first step which I mentioned, you add the redundancy, right? So let's say you have a nth input block, small n, lowercase, nth input block, which is basically a vector Sn, okay, and it has capital M number of symbols. Okay, so essentially it is a m cross 1 vector. So there are m unknown symbols, okay, m unknowns, okay, m symbols, basically m symbols. These are the symbols which are actually transmitted, and at the receiving end I want to recover them, estimate them. Okay, so these are the unknowns in my problem. Okay, so this, you are adding redundancy on top of that. Add mu zeros. So this is the zero padding which you are doing. So this is the redundancy. Redundancy. Extra, zeros that you are adding. So this results in a modified vector of a larger length. What's the length now? It is m plus mu upon addition of mu zeros. So it becomes a m plus mu cross 1 vector, and m plus mu is actually equal to n as per the notations that we have seen in the lectures. So what essentially you are doing is you have this s of n and you are adding zeros. Let me use some other color for that. 0, 0, so until 0. Okay, so these are mu zeros. Okay, so this is this is actually the vector which is transmitted through the channel now. Okay, now I'll just okay, so this is an sorry, this is an n cross 1 vector, right? And my n is nothing but m plus mu. So this x of n is actually transmitted through the channel. We know these things. Okay, I'll go to the next page. And remember that pseudo circulant matrix, that Toeplitz matrix, that structure, that was the structure that we encountered in case of zero padding. Remember, um, that the speciality of that structure is actually, um, is what leads us to, that estimate for our transmitted symbol. And essentially there are a lot of zero entries there. So this symbol, the matrix that I'm going to draw now, it's actually a matrix of there are some entries in that matrix which are functions of z, which have the z inverse components, meaning that the z inverse terms or the memory terms, right? Those are the undesired terms. We don't want any memory because we don't want any, in, interblock interference going on, right? We just want that, okay, at that time instant, this should be that received symbol should be a function of the transmitted symbol at that particular time instant. We don't want any interference from any other time instant, right? So that's how we want to take care of the interference. So in order to do that, we need to somehow ensure that those terms in the matrix, which are the memory terms, z inverse terms, should not come to my picture, should not contribute to my uh, computation overall, when I do the matrix multiplication and all, right? So this special structure of the matrix and the way, the calculation goes, it ensures actually that thing. So I'll write it down, this CPCZ structure. CPC, pseudo circulant, remember, pseudo circulant matrix. Again, pseudo circulant, I've discussed this in detail in the previous session. So due to that z inverse terms, actually there is that pseudo circulant nature. Yeah, I mean, it's not just simple shift, simple circular shift, right? There are some z inverse terms introduced also. So how does it look like? It is an n cross n matrix, square matrix, and it has the following structure. Okay, so C naught, C1, I'm drawing column wise, C2, so on till C mu. Okay, so C naught till C mu means mu plus 1 channel taps. Okay, and the next column would be the shift. Okay, it's like this. And it goes all the way. So the elements in the diagonal, across any diagonal, they are constant. And then this C1 also, it appears along this particular diagonal always. And so this goes till C new. Okay, that's the last entry. So this is somewhere like this. Okay, and the next column would be C naught, C1, so on till C mu minus 1, right? And the next term, okay, let me give a demarcation. Let me do this I know I have drawn this in the previous session also, but there's no harm in, you know, making a practice. Okay, so this next term will be C mu, that goes upward, that gets shifted circularly, but it's not an exact circular shift, but it appears with a Z inverse term in front. So that's why pseudo circular. Okay, pseudo circulant matrix. Similarly, you can have, you know, the other terms also. So this will be I think what, C naught, so on till C mu minus 2. Now there will be two terms on the top. First is C mu minus 1 coming with a Z inverse, then C mu. Okay, and you can repeat this till C naught appears at the bottom. Okay, so all the successive terms C1, C2 and so on till C mu will now go to the top. So C1 comes here but with a Z inverse, C2 comes here with a Z inverse, and so on till C mu with a Z inverse. So see all these diagonals, these entries are constant across all the diagonals. Okay, this is how the structure looks like more or less, and you can also draw another line as follows, you know. So the reason why I am drawing this line is that, okay, in this particular quadrant, you see this quadrant, yeah, uh, all my Z inverse terms or the memory terms are lying. Okay, I want to get rid of these terms, okay, just for the sake of eliminating interference. Okay, so, and if you label this yeah, so how many uh, sorry, how many rows are there till this point? There are mu rows, right? Mu rows, and these remaining part constitutes m rows. Okay, so this part also has m columns, and this remaining part has mu columns. Okay, so overall it is a m plus mu cross m plus mu matrix, and m plus mu is nothing but capital N, so it's a n cross n matrix. Okay, right, fine, this is fine. So by the way, the entries that I have not drawn, I mean the entries that I have not written are actually zero. Okay, that's why I have not written them. You can very well understand, right? So it's fine. And remember, now in the lectures we have seen the relation in terms of the Z transform as well. So I use the S of n and x of n in the time domain. Okay, this is, by the way, this is it's a vector. So the notation is like, it has a Z transform which is Now it's a Z transform of a vector, right? So that it's element wise, you know, they will get delayed. So S of 0 times 1 plus S of 1 times Z inverse plus S of 2 times Z to the power minus 2 and so on. That will be S of Z basically. So this is S of Z. And similarly, this has this Z transform. That's the standard notation. And the received signal is related to that transmitted vector x of n as follows. So this is the matrix CPC of Z that I just drew here times x of Z. Okay, and as I was saying, due to the special structure of this matrix, what happens is that if you actually multiply CPC of Z with x of Z, you can take, right? You can take the Z transform of this. It's a vector. So then what happens is that it ensures that the observation is that you kind of have a memoryless system relation. So input output relation, meaning that your R of I will depend only on S of I. Okay, so those contribution from those memory terms, these Z inverse terms, are taken care of. So those terms are, you know, cancel out. They don't have any contribution in the overall relation. So if you take this R of n, it turns out to be a n cross 1 vector, because x of n that you transmitted through the channel was also n cross 1 vector, right? This, see, this n cross 1 vector, and this is actually related as follows: C low times S of n, and S of n is a m cross 1. S of n is m cross 1. Initially we saw here, right? M symbols in a vector. So how am I arriving in this step is basically, if you see, x of n is containing S of n and some mu number of zeros, right? So if you compute x of z, you already have some S of z and some terms, right? There are, rest of them are redundant zeros, so they won't have any contribution. And what is this C low? By the way, C low will have a actually dimension n cross 1. So n cross m times m cross 1 gives you n cross 1, which is actually the case in LHS. So LHS and RHS are dimensionally correct. And what is this C low? C low is basically the part of that CPZ matrix which I have drawn here, ignoring this memory part, meaning that this, so why does this color keep changing? Okay, just a second, right? Can I increase the thing? Yeah, I can increase. Yeah. So this matrix, this matrix, sorry for this last thing, okay, like this. Okay, so this indicated in this orange, this portion is actually the one I'm looking at. Okay, so this part is actually your C low. This portion is your C low matrix, which is a n cross m order matrix. There are n rows and m columns. What I'm essentially doing is I am getting rid of this memory part here. So this all these z inverse terms here. So I'm getting rid of those terms. So these terms actually. Okay, so this is how you can partition the matrix into two parts actually. The memory, one part with the memory and the other part independent of the memory. So this is the memory part. It's the memory part. This is the memory part. Sorry, I need to change the color. This is the memory part. And to be removed, actually, we want to be removed. So the dependency on this part is removed. So dependency on the memory part is removed, and that's how I can get rid of the interblock interference. So this R of n is basically my output vector or the received vector, whatever you like to call it, or received vector, whatever. So and it turns out that okay, here I have, like, in this received vector, how many symbols are there? Capital N. How many unknowns did I have initially? M unknowns, M symbols that I'm initially sending, right? Before even adding redundancy. So M unknowns and capital N equations. So, and capital N is greater than capital M, because we know that capital N is capital M plus mu. Mu is the number of redundant zeros. So we have an overdetermined system of linear equations, and that can be solved using the pseudo inverse approach based on least squares. So what we have is overdetermined system of linear equations. If you would have n equations, n unknowns, it's fine, you can solve it using the standard method. Yeah, then you would have actually have a solution, provided, I mean, the matrix is invertible and all. But here it's a different scenario. So here you have capital N greater than capital M. So capital N is actually the number of equations that corresponds to the rows of the received vector, basically capital N entries, and capital M is my number of unknowns, which is the number of symbols, originally transmitted symbols. So this is now So this is actually can be solved using pseudo inverse. That's why we are going for pseudo inverse approach, based on, because the C low matrix, you see the C low matrix here is a rectangular matrix, it's an n cross m matrix, so it's not invertible straight away. So that's why we have to go for pseudo inverse. Okay, can be solved using pseudo inverse, based on least squares. Okay, that's the least squares um, solution. Okay, so what you will get is S of n, it's the estimate. Okay, it's the estimate of the input signal vector is given as that C low you are taking, C low Hermitian, or you can use dagger as well. Dagger is also transpose conjugate. I think in the lectures we have used dagger notation, but since in the other question in today's session I have used Hermitian. Hermitian also means transpose conjugate, so I'll stick to Hermitian only. This times, so this whole inverse times C low Hermitian again times R of n. Okay, this is a solution. This is a solution, and this, and you can check these are dimensionally correct, and this also had a name, pseudo inverse, more specifically Mood Penrose pseudo inverse. Okay, so I hope you can now recall those contents clearly. Okay, great. Right, so zero padding is the answer to our question, and I think it was option A, block transmission with zero padding. Yeah, so our answer is option A. Now going to the sixth question. Okay, the sixth question is a little bit numerical question, and in fact we have seen such examples during the lectures also. So read the question. Okay, we are given a communication system with the following attributes. Number of subcarriers is equals to 1024. There are different choices of modulation scheme: BPSK, QPSK, 16 QAM, 64 QAM, 256 QAM, 1024 QAM. So, you know, the constellation size is increasing, the number of bits per symbol is increasing as we move from BPSK to 1024 QAM, right? And I hope you are familiar with this modulation schemes, right? How the constellation diagram looks like. BPSK is binary phase shift keying, QPSK is quadrature phase shift keying, QAM is quadrature amplitude modulation, and so on, right? Uh, okay, so these are the choices of modulation schemes, and we have forward error correction FEC codes. There's some block codes of rate half, rate 2/3, rate 3/4, rate 5 by 6, right, so four options, four code rates to be chosen from. So there are 4 different options. Okay, 4 error correcting codes you have with different code rates. So in FEC terminology, this code rate is actually the ratio of the message symbols, number of message bits or symbols to the number of to the block length actually. So it's usually denoted by k and n. K is the number of message bits and n is the number of is the block length that is transmitted. So basically you encode k bits of message into into an n block data by adding some redundancy, and you add basically n minus k, the remaining n minus k redundant bits, which are also known as parity bits. So the ratio k by n is actually called the code rate. So those values are specified: half, 2/3, 3 by 4, 5 by 6, and so on. Duration of one OFDM signal, basically OFDM symbol, without cyclic prefix is 15 microseconds. Okay. Bandwidth, so BW is bandwidth expansion ratio is 14 by 13, and we have seen bandwidth expansion ratio. It's basically it quantifies the amount of redundancy that has been introduced. So you remember that that ratio, n by n, capital N by capital M, that ratio. Capital N is basically capital M plus mu, and the ratio of capital N to capital M is actually your bandwidth expansion ratio, because that's how you're expanding, right? By adding the redundancy, adding mu number of redundant symbols. So that is obviously greater than 1 because the numerator is greater than the denominator. So we have 14 by 13. Given this attributes, what is the minimum throughput of the above system? Now what does it mean? It means what is the minimum throughput rate using the most robust scheme. Okay. Okay, so there are actually two elements, two aspects to this. If you are going for a robust scheme, or a more reliable scheme, um, you will have the minimum throughput in that case, right? And on the other hand, there could be another option. You can go for the particular choice which gives you maximum throughput. Okay, and why in this case we want to look for the most robust scheme? Now if you recall, like, the basic idea of the Shannon's theorem also, in a channel, the information can be reliably sent with arbitrarily small probability of error at a rate which is less than the capacity of the channel. Okay, correct. um, so that's the idea of reliability, and we are looking at that particular scenario in this question, and we want to obtain low probability of error, or low, in this case, like, these schemes have multiple bits. For instance, 1024 QAM has how many bits per symbol? So log base 2 of 1024 means 10, right? 10 bits per symbols. So um, what was I saying? I just lost the flow. So yeah, I mean, so we are looking at the, I mean, symbol error rate, the scheme that minimizes, that is optimum with respect to the symbol error rate. That's what we are looking for. That's why it's more robust, because it minimizes the bit error rate, or the symbol error rate in this case, gives me the best performance in terms of that. So for that, I'm compromising on the throughput. Okay. But if I want to achieve higher throughput, then okay, I can go for others for a different choice. That we will see in the second in the seventh question, next question. But I hope you get the idea, right? Here we are looking at the robust scheme, more reliable scheme. For that, we want to have the best symbol error rate performance. Okay, the most ideal performance. And first thing for that, we need to choose now. We are given this set of options. You have this set of modulation schemes. You have this set of codes. Which one do you pick? That's the question. And we have seen in the lectures also, Professor David has worked out multiple examples, I think. And in this case, since we are concerned about the optimal bit error rate or symbol error rate performance, we know that BPSK has the lowest or the most optimum lowest bit error rate performance, symbol error rate performance. Basically, in BPSK, the one symbol has only one bit, right? There are only two symbols, and 0 and 1, minus 1, 1, whatever you like to label. So there are only two symbols, and it's a bit error rate, symbol error rate, the same thing. So it has the best performance. Okay, out of all the given options. I mean, QPSK also has similar, but as you increase the constellation size, if you go from 16 QAM to 64 QAM to 256 QAM to 1024 QAM, your bit error rate or symbol error rate performance drops actually. Why that drops? I mean, one intuitive way to visualize it is that as you are increasing the constellation size, there will be more symbols in the constellation, and they will be more crowded, right? They will be more crowded, they will be more close or adjacent to each other. So essentially in AWG, in the noise, the Gaussian noise that is in each of the symbols, so if they're close to each other, then they can um, overlap, so the noise can interfere. So that's why the bit error rate, there is chance of error. That's why the bit error rate performance is poor in the ones in the modulation schemes which are of higher constellation size, like the 1024 QAM. Okay, the 1024 QAM will have the worst bit error rate performance. I should say symbol error rate performance, because we are looking at symbols which are 10 bits per symbol and so on. So that is the idea. Okay. um, I'll first write down the information that is provided to us. Okay, number of subcarriers is equal to 1024. Basically the data subcarriers. Okay, if it's not specifically mentioned, you can assume, okay, these are the subcarriers which are available for transmission of data. In general, sometimes in the question it can be specified like, okay, these out of all the subcarriers, only certain subcarriers are meant for transmitting data. Okay, so keep that in mind. In this question, these are all data subcarriers. And now modulation scheme, the choices in hand. Modulation scheme, what are the choices? BPSK, QPSK, 16 QAM, 64 QAM, 256 QAM, and 1024 QAM. Okay, forward error correction, code rates. So R equals to half is there, and it's basically in decimal 0.5. R equals to 2/3 is there, which is 0.67. R equals to 3/4, which is 0.75. And finally R equals to 5/6, which is 0.83. Okay. Duration of one OFDM symbol and it is mentioned without cyclic prefix is equals to 15 microseconds, 15, which is nothing but 15 into 10 to the power minus 6 seconds. Okay. Bandwidth expansion. So bandwidth, so BW expansion ratio is basically the measure of the redundancy, right? That is equals to 14/13 given, and as per the notations that we have encountered, it is the ratio of n and m. So m plus mu, that is n, and in the denominator we have m. Okay. Okay. Now to pick the robust scheme, most robust scheme. So now you have to decide which modulation scheme and which code rate you want to go with. So these are four different error correcting codes sitting here corresponding to that four different rate values. So now you have to choose. Okay. So for this, for in order for you to appreciate what I just mentioned, I have another document here just for you to get some idea. Can I zoom it? So you see, that's what I was actually telling. Yeah, I think it's too big now. Yeah, yeah. I hope you can see it. So these are some important plots taken from the internet. So you see, as I was saying, this is a plot of symbol error probability versus ES by N naught in the horizontal axis indicates the SNR and it's in decibel. So it's a symbol error probability versus SNR plot. And for different modulation schemes, it has been plotted. And you see that as you go from left to right, the leftmost indicated in sky blue is the one for BPSK, and that has the best performance. You see, that has the best performance relative to the other schemes, because for a particular value of SNR, it has the lowest symbol error probability, right? Similarly, if you go to the right, you see this yellow plot which corresponds to QPSK. Okay, and then if you further go towards the right, you have 16 QAM, you have 64 QAM, and so on. These are just some of these schemes. Like you can also extend it till 256 QAM, 1024 QAM. But the idea is that as your constellation size grows, this curve shifts to the right. Okay, I mean the bit error rate performance deteriorates as you increase the constellation size. And the reason is I have already mentioned why is it so. Okay, and mathematically you can also check, mathematically you can also calculate in terms of the error function. You have the Q function and all. The symbol error probability can be expressed in the form of a Q function. You can draw the constellation and you actually take the situation when will be error, and this is in presence of AWG and noise, of course. So that's how actually we get that e power expression. That's how you arrive at the Q function expression. So for the BPSK, it will have the best performance, and as you keep on growing the constellation size, performance will deteriorate with respect to symbol error probability. Okay. So from this diagram also, the best choice for us is the BPSK, because that's the best. That's the one which delivers the best performance with respect to symbol error rate. So BPSK is the most robust scheme. Okay. And now what about the choice of the rate, choice of the code rate? We have 4 different codes also, right? 4 different codes also, right? So I have some other plots also. So why do we do this in forward error correcting codes? What we do is basically we are adding redundancy. Let's say I want to send one single message bit 0, bit 1 through the channel. It can get flipped. Okay, it can get erased also, but if you have a bit flip channel, it can get flipped, like and there is a chance that you will decode it incorrectly. So in order to take care of that, we add some extra parity bits. There are some codes called repetition codes. So instead of sending a single 0 or a single 1, you, let's say, take a repetition of 3 zeros or 3 ones as a string and then send it. Because if you send 3 zeros, if you first encode single 0 to 3 zeros, so that means it's a k equals to 1, because there is one message bit, and you are encoding into 3 bits, so n equals to 3. So the usual standard notation is an n comma k code. So it will be a 3 comma 1 repetition code, because we are repeating the message bit. So the idea of repetition or the addition of those extra 2 bits is that as the 000 travels through the channel, even if one of the bits get flipped, still at the receiver you can follow a majority decoding rule to observe that, okay, only one bit got flipped, but the remaining ones are the ones which are matching with each other. So you will make a decision that, okay, the chance is that the original message bit that was transmitted was 0, because only one bit got flipped, and that way you'll be able to decode it to the right one. So similarly, for 1 you encode it to 111. At the receiver, if you get one of the bits getting flipped, let's say 110, then you will observe that, okay, one of the bits got flipped. Since there are 2 1s, majority logic says there are 2 1s out of 3. That means the original message must have been bit 1 which was transmitted, so we'll be able to decode it correctly. So that's how redundancy helps. Okay. um, and you see this diagram here, this is a bit error probability versus SNR diagram, and what it shows is that there are 2 plots. One is without coding, and this is for BPSK. That's why we have bit error probability. It's one symbol has just one bit in BPSK. So if you look at the upper plot, it is without coding, means no coding or no redundancy has been added. It's the situation where I have one message bit, I simply transmit that through the channel without adding any protection of any parity bits or anything. So in that case, it's like, um, what should I say, it's a 50-50 chance that you can either decode it correctly, or you can decode it incorrectly. So that's a worse situation. So that's why you see the bit error rate probability curve there is on the higher side. It has poor performance. But on adding coding, you see that this curve shifts on the lower side. So meaning that Now if you choose, if for a particular value of SNR, if you draw a straight line, a vertical line like this, then what you will observe is that the bit error rate probability curve with coding has a better bit error probability. I mean, it has a lower probability of bit error for the same SNR as compared to the scenario without coding. So that's how coding is helping. And this gain also, this difference between the two curves, as you see, it's specified in dB. For this particular point, it is 1.33 dB. For this particular, as you increase your SNR, you see the difference grows. The difference is more prominent. So at the higher SNR, you have a coding gain of 2.15 dB. So that's a significant improvement. So that's why in our question we have been given different choices of the codes, right, with different rates, k by n ratio. So so um, so you see that and in fact I have another plot also. So this is also taken from the internet, and you see for different code rates, I think this is for a BPSK scheme only, a performance has been plotted of bit error rate. So you see that the code rate half has the best performance. So the code rate value, which is the lowest one, which is half, has the best performance, followed by 3/4, followed by 2/3, followed by 3/4, and followed by 5/6. So the code rate which is maximum, which is 5/6, has the worst bit error rate performance. And the code rate which is the minimum out of the four, which is half, has the best bit error rate performance. Why is the case? Because you see, as if the code rate is equal to 1, it means that the number of message bits and number of parity bits are equal. Sorry, the number of message bits and the block length also are equal. That means you are adding zero parity. You are not adding any parity bits. You are not providing any redundancy to protect your message bits. So that's why they are more susceptible to errors, right? The idea of adding redundancy is to protect your message bits, correct? So as I was giving the example of the repetition code, if you simply just transmit bit 0, bit 1 without encoding them into some 3 bits, right, you will have like 50% probability of error. But that gets minimized if you do the repetition scheme. I mean, if you add some extra 2 zeros also, take or extra ones also, then as it passes through the channel, the probability of error overall reduces. And based on the majority logic, right, it works. So that's the idea of adding the redundancy to improve the error performance. Okay, so from this plot also you can pick that, okay, the code rate of half, the code that corresponds to code rate half is the one which is the most robust in terms of bit error rate performance. So I'll go with that. So I hope you got the idea. That was the intention of this of these plots, showing you these plots. So uh, for the robust scheme, okay, which modulation scheme we decided? BPSK, best performance, best BR performance. The scheme with BPSK modulation and lowest code rate. Lowest code rate means there will be difference between k and n ratio, right? I mean, the there will be difference between the number of message bits and the number of encoded bits, the code length. So there is significant amount of redundancy that has been added. So you are protecting your message bits. So adding redundancy helps in reducing your bit error rate or symbol error rate. So that's why lower code rate uh, optimizes your error performance. So the scheme with this configuration will be the most robust scheme. I mean optimum symbol error rate or bit error rate, okay, whatever. ACR is symbol error rate, BER is bit error rate. So therefore the choice is choose BPSK and the code with rate half, because that's the minimum value. Okay, now we will compute the throughput for this scheme. For this robot scheme we need to find the throughput, and the formula for throughput is we have seen throughput. So there are a lot of terms that will come into the picture, and this is the case where we obtain the minimum throughput. So there is a trade-off. Here we are optimizing the error performance. That's why we are lacking on the throughput. Okay, as we go on the higher throughput side, we'll have to compromise on the error performance then. Okay, so throughput is actually okay. First of all, we have to see number of subcarriers. How many data subcarriers are there? So in the question, I think it is 01024, that because those many subcarriers are carrying your data times the code rate. Okay, so in this case it is half. I think I should wait. It's actually a very long expression. Since I'm writing in words, that's why it will take some space, significant amount of space. So I'm writing from the left. Okay, throughput, that's the minimum throughput that we are obtaining for the robust scheme here, is equal to number of subcarriers times code rate. Okay, because code rate is the ratio of message bits to, I mean the fraction of the message bits out of the total block length. So the message bits are only carrying the message, right? So that's why they will occur in the expression of throughput times times the bits per symbol. So for different modulation schemes you will have some number of bits per symbol, right? For BPSK there is only one bit per symbol, so number of channel bit per symbol, per subcarrier symbol. Okay, so because I want my throughput in bits per second, right? So therefore I have to go from symbols to bits. For example, if I have QPSK, I know there are 4 symbols and each symbol has 2 bits, so 2 bits per symbol, like that, times what else will be there. Okay, now okay, there are, I know there are some number of bits per symbol, and I also have to see how like and I also have to see like the duration of the OFDM symbol, right? Correct. So one subcarrier symbol divided by duration of one OFDM symbol. Okay, I mean, what I am doing here is that from the constellation or from the modulation, I have this number of bits per symbol. Okay, and each OFDM symbol is also, having some duration, right? And in this question, I think it's 15 microseconds or so. Yeah. So one subcarrier symbol will actually last for the 15 microseconds. Okay. So that I'm taking care of here. And one subcarrier symbol will have those number of channel bits, because I at the end of the day I want to express in bits per second. I mean that's how I want to express. And also one more thing that will be there is the reciprocal of the bandwidth expansion factor, 1 by bandwidth expansion ratio. Why the reciprocal of bandwidth expansion ratio? Because if you go back to the definition of bandwidth expansion ratio, it is n by m. So it's actually a measure of redundancy, because this you're adding mu symbols to your m data symbols to get capital N symbols that you are transmitting through the channel. So this would be a fraction greater than 1 surely, but in the denominator we have, if we take the reciprocal of the bandwidth expansion ratio, it becomes m by n. So m by n means the number of data symbols divided by total number of symbols after adding redundancy. So it indicates m by n, which is the reciprocal of bandwidth expansion ratio, indicates the fraction of your data symbols. Correct. And that's what I am interested in, because the data symbols are only carrying the data. So for throughput computation, it will be required. So that's why I have to take its reciprocal. Okay. Basically m by n. Okay. Now we have everything in place. So this, let's do step by step now. First is number of subcarriers, which is 1024 in our case. Code rate, we picked rate equals to half for the most robust one. Number of channel bits per subcarrier symbol, since we picked BPSK has only two symbols, right? 0 and 1, and each symbol has one bit only. So one channel bit per symbol. So this is basically 1 times one subcarrier symbol per duration of OFDM symbol. And what's the duration of OFDM symbol? It is 15 microseconds, right? So 1 by 15 microseconds means 15 into 10 to the power minus 6 seconds times the reciprocal of bandwidth expansion factor, it is 13 by 14. Okay, this much bits per second. In numerator we will have number of bits, and in denominator we will have seconds, because we have expressed the duration of OFDM symbol from microseconds to seconds by doing this, adjusting by this factor of 10 to the power minus 6. Okay, just a second. So this, if you calculate, will give you approximately 31.70 megabits per second. So basically this 10 to the power minus 6, actually 1 by 10 to the power minus 6 means 10 to the power 6. So that gives you megabits per second actually. So if you do the calculation, you get this value, and so 31.70 matches with the first option, option A. So it's a relatively low value of throughput, and you can do the comparison if you now solve the seventh question, because in the seventh question you are asked to choose the scheme that maximizes the throughput. Okay, now you have to decide the specifications, decide which modulation scheme and which code rate to pick, so that your throughput is maximum, you obtain the maximum throughput. And in this case what we'll do, now you're not bothered about the error performance, you want to enhance the throughput. So obviously what you will do is you will go for more number of symbols, right? You want more data. So if you go for higher constellation size, they will have more number of symbols which will carry more amount of data. So for example, the 1024 QAM has 1024 symbols which will carry, and each symbol will carry log base 2 of 1024, which is 10 symbols, correct? So that's the choice there, because you will have more bits per second throughput in that case. And similarly for the rate also, the code basically, you now have to go with the code with the higher code rate, because you want the throughput to be maximum. So k by n ratio, the ratio of the fraction of the message symbols, right, that you want to be high now in order to maximize your throughput performance. So that's why you choose the code with the maximum code rate, which is actually 5 by 6. And for the modulation scheme you choose 1024 QAM. Got it? So here for maximum okay, for maximum throughput, we choose the scheme with the higher constellation size, 1024 QAM, and because since more data bits per symbol, right, that's what we want, more data rate, and highest coding rate, highest code rate. Okay, but this will compromise on your um, symbol error rate or bit error performance. So this compromises with this, however, compromises with the ACR or the BER, bit error rate performance. So there's a trade-off. Okay, which is straightforward. And so uh, what are the choice that you are making now? Now we'll go to the next page. So 1024 QAM, right? That's what you choose. So we choose 1024 QAM, and we also choose the code with rate maximum, which is 5 by 6. this is 5/6. So throughput in this case, again using the same formula, just the values would be different, and in this case we will obtain maximum throughput. That would be number of subcarriers again remains 1024. Code rate now becomes 5/6. Now we have, okay, now for 1024 QAM, for 1024 QAM, how many bits are there in one symbol? It has log base 2 of the constellation size, which is 1024, that is equals to 10 bits per symbol, correct? So 10 channel bits per symbol, so this is 10, and one subcarrier symbol in 15 microseconds OFDM duration, right? So that remains same. So one subcarrier symbol in an entire duration of an OFDM symbol, which is 15 microseconds, and from microseconds I can go to seconds by adjusting this factor, times the bandwidth expansion factor's reciprocal, which is the same as 13/14, it stays the same. So, and now if you, and by the way this is in bits per second, and if you simplify this you'll get 528.25 megabits per second. So you see there is a significant improvement. That's the maximum throughput that you obtain. In the previous case you got 31.7. Here you got 528.25 megabits per second, right? So, and it matches with the option B. Okay. Now quickly go to the next one. What is the center frequency of this 802.11a? So this 802.11 is actually a wireless network standard that is set by the IEEE committee. So it's yeah, and so and there could be different specifications depending on whether it is 802.11a or 802.11g, 802.11b, and so on. There are multiple standards, and they will have different specifications, but for this and we have seen this in the lecture also, that for 802.11a it is centered at around the 5 gigahertz frequency. Okay, similarly you could have 802.11g, which is centered around 2.4 gigahertz frequency. Okay, so that's just the speculations, sorry, specifications, my bad. So this is just factual information. So 802.11a is centered around 5 gigahertz. So 5 gigahertz is your answer, and it is actually option A. And there could be other standards also, like I mentioned 802.11g for instance, that is centered around 2.4 gigahertz. Okay, and there could be others also. So our answer is option A. Okay, now coming to the last question for today, I believe so. Yeah, so it is known that a channel has 10 discrete tabs. What would be the minimum length of cyclic prefix? CP stands for cyclic prefix in tabs. This again, I think we have covered this before also. So what it says is that there is a channel which has 10 discrete tabs. Okay, so 10 channel tabs are there, and we know that if there are 10 channel tabs, then the number of symbols of ISI would be 1 less than the number of channel types. So that will be 9. Okay, 10 minus 1, 9. 9 symbols of ISI. And the requirement of the cyclic prefix is that the length of the cyclic prefix should be at least the length of the number of symbols of ISI, which in our case is 9. So the minimum length of cyclic prefix should be 9. Option B. And what is this cyclic prefix? Basically, it's a technique that is deployed in OFDM in order to avoid this or minimize this inter-symbol interference. That's the idea actually. That's why you need the minimum length of the cyclic prefix to be the number of the ISI symbols. What you do is basically, if you have a stream of data, you take the last some set of symbols and copy it to the uh, copy that or append that in the front of the entire data block. So that way you actually get a guarding actually. So that way what happens is that if there are two adjacent blocks also of data, even if they interfere, you still have your original data that is not compromised, that is not getting overlapped and not getting interfered. You get the idea, right? I mean, I'm not sure if I am able to make you understand or not, but that's the idea of cyclic prefix. So the length of cyclic prefix should be at least the number of ISI symbols, which is one less than the number of channel taps. Okay, why one less than number of channel taps? Because usually in a multipath environment, what you have one desired signal, uh, and the rest of the components are the components arising out of the multipaths, right? So altogether you have some mu plus 1 channel taps, where that additional one is actually the one which is the desired. So the remaining mu ones are the multipath taps basically, or the number of ISI symbols. So yeah, okay, so the solution to this is, let's say if you have a channel C of Z which has mu plus 1 channel taps. So Ck, the coefficient, times z to the power minus k, and k runs from index 0 to mu. So 0 to mu captures mu plus 1 coefficients or taps. So meaning that number of channel taps, by the way, this hash is just a short for number of. So number of channel taps is mu plus 1. In our question it is 10, and so this mu plus 1, this plus 1 is actually, you can think like, okay, there would be a C naught term also, right, which won't have any delay component. So that's, you can think of it as a line of sight, the desired component, signal component. So that's your desired component, and the remaining mu terms will have some delay component. So it's like, yeah, so so that those delay components are arising because of the multipath uh, things. Okay, multipaths basically, the reflected paths and so on, instead of the non-line of sight components basically. So those will contribute to your ISI. So you have, out of mu plus 1 channel taps, you have mu symbols of ISI, and one is actually the desired one. So number of ISI symbols is actually mu, which is number of channel taps minus 1. This is known to us. And the requirement of the cyclic prefix says that length of CP is cyclic prefix, should be at least the length of the number of ISI symbols, which is actually mu. Okay, So, and in our problem, the number of channel taps is how much? It is 10, right? Now we go to the question, what is given? 10 discrete channel taps. So mu plus 1, that is given as 10. Okay. And which means, what is my number of ISI symbols? You take number of channel taps minus 1, so that is mu, and that is 9. So 10 minus 1 is 9. So therefore at least a length 9 cyclic prefix is required. Length of cyclic prefix is at least mu. Okay, so this gives me length of CP is at least 9. Okay, so therefore minimum length of cyclic prefix is 9, and it matches with option B. Okay, so with this we have arrived at the end of today's session, and I'd like to conclude the session today, and I hope you are able to follow all the things. It's just a straightforward, recap of the contents, nothing else. And we'll meet again on next Friday 6 p.m. So that will be the 12th session, and it will be also followed by another extra session on Thursday, which is 18th of April, I believe. So yeah, so 2 more sessions, I think. Okay. Okay, so I'll sign off, and thank you everyone.